systems. So I'm going to discuss everything in the very simple case of two polynomials and two variables. We're going to look at two polynomials and two unknowns. For example, the following, with the understanding that everything I say will generalize to n polynomials and n variables, okay? And I'm going to look at an example. It's our running example. So I have a polynomial g, a1 plus a2x plus a3xy plus a4y. And the second polynomial h is b1 plus b2x squared y plus b cubed xy squared. And the 7 coefficients are parameters. So the ai and bj are parameters. Okay? So the question is, suppose these parameters, these coefficients are random numbers, real, complex, rational. How many solutions does such a system have? And the first thing that most students would try is to apply Bazoo's theorem. So Bazoo's theorem suggests that in this case, the number of solutions is 6. So we would expect 2 times 3 common zeros in the projective plane over an algebraically closed field, right? Because the first equation has degree 2, the second equation has degree 3. Bazoo's theorem says the general quadric and a general cubic in the plane should meet in 6 points. Okay? Now, here we have a specific sparsity structure, and we want only solutions that have non-zero coordinates. So it turns out that some of these solutions will lie on the coordinate planes, but we're going to only be interested in x and y that are non-zero. X is a non-zero complex number and y is a non-zero complex number. So we're interested in solutions in the algebraic torus. Okay, so this object here is called the algebraic torus, and this is going to be our basic ambient space today and tomorrow. For the visitors at KAIST, there's an active research group in toric topology. Find out who they are. Talk to them. So we have an algebraic torus. Why is this thing called a torus? Well, C star can be thought of as R plus times S1, right? A non-zero complex number has an argument and a phase. And we have 2 copies of this. So this is an equality. This is an isomorphism of multiplicative abelian groups. They are the same as an abelian group. And we can rewrite this, of course, as R plus squared times S1 squared. And that's why it's called a torus. Okay, so this part, S1 squared, is a torus. So that's why we have a contractible part and a torus. So the reason this is called an algebraic torus is because the non-contractible part is indeed a torus. Okay? So we're interested in solutions in the algebraic torus, C star squared. Well, it turns out that our system has 4 solutions in the torus, 4 distinct solutions. In C star squared, provided a certain non-degeneracy condition is satisfied, provided the so-called mixed discriminant is non-zero. Okay, and I'll tell you what the mixed discriminant is in a moment. That's a certain non-degeneracy condition. You can Google this. So if, like Vissarion, you're very bored by what I'm saying, you can get your device out and Google mixed discriminant, and you get to a paper which you're encouraged to read. So the mixed discriminant is non-zero, so it's a certain polynomial delta, depending on f and g. And the leading term is 4 a1 to the 7, a3, b2 cubed, b3 cubed, plus many more terms. Okay, so it's a polynomial with a fair number of terms. It has degree 14 in the coefficients. It's bihomogeneous of degree 8, 6. It has degree 8 in the coefficients of G. It has degree 6 in the coefficients of B. And you can find this polynomial on page 36 in the lecture notes on solving polynomial equations. Okay, so how do you find such a discriminant? So that's a quick reminder on what we learned about elimination last week. So how to compute this? How to find this? By this I mean this discriminant. Well, what you do is you eliminate x and y. You calculate the elimination ideal from the following. So you form the ideal that has g and h and the Jacobian. So the derivative of g with respect to x, h with respect to y, g with respect to y, h with respect to x. So this is the Jacobian of our system of two equations in two variables. Now this is an ideal in a polynomial ring in 9 variables. a1, a2, a3, a4, b1, b2, b3, x and y. So we look at this ideal in a polynomial ring in 9 variables. Then we saturate by x and y, the product of x and y, because we want to remove zeros where x and y, we're removing points where x and y are non-zero, and this is the true incidence correspondence after the saturation. We now have the incidence correspondence of points x, y, and parameters a and b, such that x, y is a multiple point of the system. Then you eliminate, and you get the principal ideal generated by this equation. Okay? People are sleepy this morning. Is that clear? Michael, completely clear? Okay, so the Jacobian vanishes at a given root if it's a multiple root, and that's how we get the equation, the discriminant. Now why 4? Okay, that's the second question. So why is the number of solutions 4? Well, the answer is, let's consider Newton polygons. Okay, so based on the Newton polygons and of our equations, we can derive the number 4, the number of solutions in the torus. So let me give you a little bit of notation just on polytopes. Again, this is going to be boring for some, but maybe a little less for others. So just a few definitions. So a polytope is the convex hull of a finite subset. I'm going to call A in R to the n. So if we're in n space, every polytope, so the polytope, has faces. A face of a polytope is a subset at which a linear functional attains its minimum. And these faces can have various dimensions. They themselves are polytopes. So they can be of dimension 0. Zero-dimensional faces are called vertices. They can be of dimension 1. One-dimensional faces are called edges of the polytope. Well, they could be of dimension d minus 1, right? So let's say d is the dimension of the polytope. A polytope, so d is the dimension of the polytope, d minus 1. These are the facets. So we have a d-dimensional polytope in n-dimensional space. The d minus 1-dimensional faces are called facets. And then the d minus 2-dimensional faces are called ridges. Okay? So we have, so to have, and of course the full polytope is also a face, right? If we take the zero linear functional, the polytope, the subset that minimizes the zero functional is the polytope. So the polytope is a face of itself. Okay? So you can see to have all of these distinct, right, in 3 dimensions, the edges and the ridges are the same for a 3-dimensional polytope. So the first interesting case is in dimension 4. So don't even bother with 2 and 3-dimensional polytopes. Always start in dimension 4 when you draw and study polytopes. But just to kind of warm up, a little question for you. So how many faces does the 3-dimensional cube have? How many faces does the 3-dimensional cube have? So Feng, what do you think? How many faces does the 3-dimensional, this is affinely isomorphic to the 3-dimensional cube. How many faces? Hmm? 20? 6, 8, 20, 6 plus 8, 14. Many opinions. How many faces does a 3-dimensional cube have? 27, 16, 12.
27, right?
27 is almost correct. Yeah. So 27 is a little bit. Okay. So there's a small opinion. Okay. So there's sort of, it could be either 26 or 27. Okay. So my opinion, it's 26 because I do not allow the empty set. Let's disallow the empty set. There are 26 faces, right? There are 8 zero-dimensional faces. They're called vertices. Okay. There are 12 one-dimensional faces. They're edges or ridges. And then there are 6 two-dimensional faces. And then there's the polytope itself. So 8. So that's 8. Let's try. So that's the 27. 8 plus 12 plus 6 plus 1. 27. Sure. Just like the number of trees. Isn't that amazing? Okay. 27 trees on a cubic surface. Okay, how about the 4 cube? How many faces does the 4-dimensional cube have? What do you think? So now we have vertices, edges, ridges, and facets. Every facet is a 3-dimensional cube. Every ridge is a 2-dimensional cube. Every edge is a 1-dimensional cube. Every vertex is a 0-dimensional cube. How many faces altogether? Yeah, 80. Okay, if we believe that the answer here is 27, then better the answer here be 81, right? So they are indexed by ternary strings of length 4, right? So you have a ternary string whose letters are plus, minus, or star, right? That's indexes the faces. Okay. Very good. So typically in our applications here, the set A that we take the convex hull of not only is in Rn, but it's actually in Z to the n. So in that case, we talk about the convex hull of a set of lattice points is called a lattice polytope. So when I say a lattice polytope, I mean a polytope whose vertices are lattice points. And for a lattice polytope, the volume, well, the ordinary Euclidean volume is 1 over 1 factorial times an integer, non-negative integer. Okay? So sometimes we ignore this factor, and I'll try to be precise about this, okay? Now, polytopes are nice. Spectrahedra are better, okay? I know it's very nice and charming and great and wonderful to study tropical geometry, and I'm for it. I'm part of it. But it's even better to study polynomial optimization prior to the June workshop. And likewise, it's even better to study algebraic statistics prior to the July workshop. So polytopes and polyhedra are nice. Spectrahedra are even better. Okay? But today and this week, we're going to stay with polytopes and tropical geometry. Okay, so in the plane, if n is equal to 2, the area of a lattice polygon is a half integer. So d is 2, so times 2, we get an integer. So for example, let's take this one. We take this triangle. We go like this. Well, there are various ways to calculate the area. But the best way is to triangulate it using an interior lattice point, and then you have 3 small triangles. So the area, 2-dimensional volume, is 3 over 2, 1.5 for this example. Okay, so we have a notion of arithmetic with polytopes. So we can define the Minkowski sum. The Minkowski sum of 2 polytopes is a polytope. Right, so if P and Q are polytopes in the same ambient space, then P plus Q, the set of all points little p in P, and this little points Q in Q is again a polytope. Okay? The reason that is so is that linear projections of polytopes are again polytopes, right? So the direct product P times Q is a polytope. The Minkowski sum is the image of the direct product under a linear map called addition. So therefore P plus Q is a polytope. The dual, the convex dual of a polytope is a polytope, right? So the dual of a cube is an octahedron. The dual of an icosahedron is a dodecahedron, and so on. Okay? So polytopes are closed under projections and under duality, and that is not the case for spectrahedra. And that's an important feature of polynomial optimization. Okay, so let's do a little exercise here. Let's take the 2 polytopes like this. Let's take the unit square. I'm going to draw in blue. That's P. Let's take this polytope Q. I'm going to draw it for you, just to kind of be very clear. That's Q. And now let's draw P plus Q. And there's nothing as good as audience participation, so I'm looking for a volunteer to draw P plus Q. Would you like to volunteer? Okay. Okay, so let's see now. You'll tell us how to draw P plus Q. So P is the blue, Q is the red, and then over there on my grid. Yeah, okay. Practice, yeah. Mm-hmm. Oh, can you draw that in red? Do you mind drawing it? Yeah, because this edge is the parallel to a red edge. Do you mind drawing?
I can't do this vertex. so I draw.
Yes, thank you. No! Oh. Can you draw? So, this is a red edge. Can you draw this in red?
So
and the blue?
This blue vertex. So I,
Okay.
Blue.
Okay. Okay.
Red vertex.
Okay.
Red edge.
Okay. Let's see what happens. Okay, you do it. What works for you? Okay.
That way. Red. Blue. And then now. Not good. Coloring.
No, now you have to be consistent. Stay consistent.
Red.
Okay, very good. Thank you. Yay! Okay, so there's P plus Q. Okay? Just for the record, so let's record the areas. So this one has area 3/2 because it can be subdivided into 3 primitive triangles. This one has area 1, right? We can divide into 2 triangles. And this one, I think, has area 13/2. We can count, right? So there are 1, 2, 3, 4 squares. That's 8, 9, 10. Okay, you figure out. So it's 13/2. It's 6.5 is the area. Okay, what about the vertices? What are the vertices or faces more generally of a Minkowski sum? Well, a face of P, a vertex of P, is a point in P at which a linear functional is minimized. Likewise here, right? So suppose you have a linear function that attains its minimum here somewhere. Its minimum here somewhere. By linearity, well, it attains the minimum at that point plus that point, right? So for example, let's say we have the point go southwest. So we want to solve the linear program called go southwest. Remember, linear programming is semi-definite programming for diagonal matrices. Okay? So we want to go southwest. Then the optimal vertex is this vertex and this vertex. And then this down here is the sum. This point is the sum of this point plus this point. Okay? So question, what are the vertices? Well, they are sums of faces, or sums of vertices. Or faces more generally. Okay? So every face is a sum of faces. But of course they have to be compatible. Right? They have to be compatible, meaning they have to maximize the same linear functional. Right? So not every sum of vertices is a vertex. So for example, this vertex, this blue vertex, plus that red vertex, that lands in the interior. Clear? So if I take this blue vertex plus that red vertex and I add them up, then in the Minkowski sum it lands here. So it is not a vertex. Right? So not every sum of vertices is a vertex. Only compatible sums of vertices are vertices. So there are 4 times 3, 12 possible pairs of a blue vertex and a red vertex. But out of those 12 pairs, 7 pairs are compatible and 5 pairs are not compatible in this example. Okay, so interested in the compatible pairs. Let's practice this a little bit in 3-dimensional space. So let's take 2 3-dimensional cubes and try to visualize the Minkowski sum. Okay? You'll have a chance to do so this afternoon. Okay? So you take the Minkowski sum of a polytope plus another polytope. The Minkowski sum is a 3-dimensional polytope. That 3-dimensional polytope has vertices. Every vertex of the Minkowski sum is a sum of a vertex plus a sum of a vertex. Compatible pairs. Every edge of the Minkowski sum is either the sum of an edge here plus a vertex there, or a vertex here plus an edge there, if they are sort of in general position. Okay? More interesting are the 2-dimensional faces. There are 3 possibilities. A facet of my Minkowski sum, a facet of my 3-dimensional polytope, is either a vertex of the green polytope plus a facet of the blue polytope, or a vertex of the blue polytope plus a facet of the green polytope, or a green edge plus a blue edge. Okay? So there are some of vertices, but there are several combinatorial possibilities depending on the dimension of the situation, and you will have an opportunity to practice this afternoon. So anybody does not have problem number 4? Problem set number 4. Okay? So try to look at problems 4 and 5. So problems 4 and 5 are very nice problems. And since I have a little bit of a printing crisis here at KAIST, I don't have any extra copies. Okay. Okay, so problems 4 and 5 this afternoon, with Jose's help, you will figure out how to do these problems, how to add polytopes in 3-dimensional space. Okay, now what's the connection to nonlinear algebra? Why are polytopes so important in nonlinear algebra and in algebraic geometry? Polytopes are an organizing principle. So if you have some complicated mess, polynomials in several variables are a mess. You look at them on your screen, they look very complicated. Grobner bases don't terminate. Basically, nonlinear algebra can be a mess and intimidating. Okay? Polytopes put some structure. Polytopes, convex polytopes, are an organizing principle that puts some that makes sense out of the combinatorial structure. So this is the concept of a Newton polytope. So given a polynomial f coefficients in a field K in n variables x1 up to xn, we define its Newton polytope. Its Newton polytope is Newt. Well, I'm going to use nu, So in the book of solving polynomial equations, there's no t. I just called it nu of g. In the tropical book, for some reason, we call it newt. I don't know. Anyway, so the Newton polytope is the convex hull of all lattice points a and n to the n, non-negative integer vectors, such that x to the a appears with non-zero coefficient in f. So the coefficient of x to the a in f is non-zero. Oh, g. F. Okay. So so given a polynomial, you make a polytope. Okay. Out of a polynomial, you make a polytope called the Newton polytope. Now that's a good thing to do because at some level, that's a homomorphism. So multiplication corresponds to Minkowski sum. Okay, so we have a homomorphism of the multiplicative semigroup of polynomials to the additive semigroup of polytopes, right? So nu of g times h is nu of g plus nu of h under Minkowski sum. Okay? So we have a homomorphism of multiplicative semigroups. We can, in fact, throw in addition, right? We can add polytopes, and we can also talk about convex hull of unions as being a kind of addition. Then this becomes a homomorphism of semi-rings. Okay? Yes?
Do you see any generic coefficient?
No, here I don't know. Any coefficient, any polytope. For any polytope. Why is this true? Okay, why is this true? So, proof. I have two polytopes. I have the polytope on the left-hand side, and I have the polytope. So let's prove it. Let's talk through the proof. Okay. So I have two polytopes. I want to show you that they are equal. Okay. Well, how do I show that they're equal? Well, one way to show that they're equal is that they have the same vertices. If two polytopes have the same vertices, they're equal. So if K gives me any linear functional, he gives me his favorite linear functional, if I can show that the vertex that optimizes his linear functional here equals the vertex that optimizes the linear functional there, then they're the same polytope. Okay? But we talked a little bit about the leading term, so let's observe the following. So if I have the initial of g with respect to w, so this is the leading form. So in the polynomial solving book, this is the highest term. In the highest terms, in the tropical book, this is the lowest terms. Doesn't matter, right? Then it's a basic fact that the Newton polytope of the initial form is the face in direction w of the Newton polytope of g. Right? Because, so this is the reason. So if you give me a linear functional here, then the vertex is the exponent vector of the leading monomial. Here it's the exponent vector of the leading monomial. But the leading monomial of a product is the product of the leading monomials, regardless what the coefficients are. And that's because K is a field. So K is a field, in particular K is an integral domain. So as long as K is an integral domain, that is to say there are no zero divisors, so as long as K is an integral domain, we have this identity. Okay, does that answer your question? And the reason is the product of the leading terms is the leading term of the product, because K is a field. Okay, let's go back to n equals 2. Let's define the mixed area. So last week, yes?
One question about this Newton polytope. If I have two distinct polynomials tangens, is it possible to get the same Newton?
Yes, exactly. So it only depends on which terms appear. It doesn't depend on the coefficients. So here, this definition of Newton polytope only remembers whether a coefficient is 0 or non-zero. That's my definition of Newton polytope. If you have friends who study number theory, they have a slightly different definition, and it has to do with powers of p and so on. But for me, the Newton polytope, all I do is I look whether a monomial appears with a non-zero coefficient or not. So then any two polynomials that have the same term appearing have the same Newton polytope. Good question. Any other questions? Okay, let me define the mixed area. So the mixed area of two polytopes, of two polygons in the plane, P and Q in the plane, is the following quantity. So note that M for mixed area of P and Q, that's the area, the usual Euclidean area of the sum minus the area of P minus the area of Q. So it's the area of the sum minus the sum of the areas. So for example, here in this case, in this example, the mixed area of P and Q well, it's the area of the sum, so 13 over 2 minus the sum of the areas, so minus 1 minus 3 over 2. Please admire my colors. And that turns out to be 4. Okay, so this is equal to 4. So the mixed area of this square and this triangle is 4, a positive integer. Okay. Now, let me redraw. So I'm sorry I criticized your colors. I understand your choice of colors by the way you constructed it, and I think it's important everybody has their own scheme. Let me redraw it one time with the reversed colors, if you don't mind. So I'll draw it a little bigger. So I'm going to use blue, for blue. And then I translate the edges over. So I go like this, like this, like this, like this, and like this. Let's try to understand the mixed area pictorially. Okay? Well, let's do the following. I can place my blue square inside the Minkowski sum. Okay, so I'm just, for example, this is a choice. For example, I can place my square here, right? So this square is this two-dimensional face plus this zero-dimensional face. This vertex plus this polygon is this point, okay? But now I can continue. So for example, there are different choices. So let's say I can have the other polygon here. Maybe. So now that's this one plus that one is this one. And now I can complete this to a so-called mixed subdivision. Okay. So now I have subdivided my polygon into 5 smaller polygons, right? Here I have 5 pieces. 1, 2, 3, 4, 5. To make this very clear, let me remove the white lines. Okay. Okay, so I've subdivided this into 5 pieces. So here I have a piece of type 2, 0, a blue 2-dimensional polygon plus a 0-dimensional red. Type 0, 2, type 1, 1, 1, 1, 1, 1. So I have 3 mixed parallelograms. So these parallelograms are sums. These are affinely equivalent to 2-dimensional cubes. A 2-dimensional cube has 9 faces. So I have 3 2-dimensional cubes, and I'm interested in the total area, right? The area of the sum, I take the area of the sum minus the blue area minus the red area. So all I need to calculate is the areas of these pieces. And well, the area of a parallelogram is the absolute value of the determinant of the 2 vectors. So this parallelogram has area 1, this parallelogram has area 1, this parallelogram has area 2. So we can also realize this as 2 plus 1 plus 1. Okay, so the area of the sum minus the sum of the areas has a representation as a positive sum of positive integers. So you asked me last week about the Minkowski, about the mixed volume in general. So we had an alternating sum for the mixed volume. In combinatorics, whenever you have a combinatorial number that's given to you as an alternating sum, an inclusion-exclusion formula, it is better to have a positive formula as a sum of positive integers. So here, the number 4 is an alternating sum, but it's better to have a positive sum. And Rainer will draw the dual graph to this graph. Right? So why don't you draw, there's a graph in the plane, yeah? So make a vertex here, and then a dual edge and see what you get. While we do that, let's state a theorem. That's Bernstein's theorem. Bernstein's theorem, and that's 3.2 in the notes. The expected number of solutions. To a system of 2 equations and 2 variables, g of x and y equals h of x and y is equal to 0 in the algebraic torus is the mixed area of the Newton polygons. So in symbols, the mixed area of the Newton polygon of G and the Newton polygon of 4 of H. So this explains the earlier results. So this was the example that we had at the beginning of today's lecture. We had a polynomial with 4 terms, 1, x, y, and xy. We had another polynomial with the constant term x squared y and y squared x. And the number of solutions is 4. So this is Bernstein's theorem. The number of solutions to a square system of equations is the mixed area of the 2 polygons, In n dimensions, it's the mixed volume of the Newton polytopes. Ah, very good. So by expected, I mean the following. So I have the space of coefficients. So this is the space with coordinates a1, a2, a3, a4, b1, b2, b3. You can think about this as a 7-dimensional affine space, but better, think about it as a P3 times a P2. So I have the coefficient space, so a 3-dimensional projective space with homogeneous coordinates a1, a2, a3, a4. And for the second polynomial, b1, b2, b3 are the coefficients. And inside this, there is a discriminant, as a big polynomial of degree 8, 6, such that in the complement of that hypersurface, the number of solutions is exactly 4. There are 4 distinct solutions without multiplicity. Okay? So colloquially speaking, for random coefficients, so for measure 0, right, if you have coefficients over the real numbers or complex numbers, so I'm sorry, for probability 1, you will have this number of distinct solutions. So there's always in algebraic geometry, there's a hypersurface of exceptional cases in the parameter space. So outside that discriminant, this is valid. Other questions? Yes, very good question.
Does this always have to be a hypersurface?
The discriminant?
Yeah.
No. So the question is, does the mixed discriminant always have to be a hypersurface? The answer is usually it's a hypersurface. Usually that's a hypersurface, but there are some exceptional cases where it's not a hypersurface. So if you go to your device and you type mixed discriminant, you get to a paper. That's a mediocre paper that talks about these things. And inside there was a conjecture about exactly which cases are exceptional, and that was more or less solved in a subsequent paper by Esterov. So if you look at discriminant, mixed discriminants by Dickenstein, Catani, Cueta, and myself, and subsequent work by Esterov, you find a pretty tight characterization. But typically, usually it's a hypersurface. Yes?
So when you're in the discriminant locus, is it understood?
No, that's complicated, right? I mean, even in one variable. So let's think about a polynomial in one variable of degree 5. Okay, so let's say a polynomial of degree 5. So outside the discriminant, there are 5 distinct solutions, right? Well, on the discriminant, typically, right, so what's going to happen if you have a polynomial of degree 5? Well, either you have 5 distinct solutions. Let me draw that by a little diagram like this. So either there are 5 distinct solutions, but on the discriminant, well, you might have, typically you have, sorry about this. There are 5 distinct solutions. I'll write it like this: 1 plus 1 plus 1 plus 1. But on the discriminant, 2 roots will come together, and you have 1 double root and 3 simple roots. So let me draw that by a diagram like this. There's 1 double root and 3 simple roots, right? But now inside you could have further degeneracies, but now you can see 2 things can happen, right? So either you could have 2 previous simple roots come together, right? You could have 2 plus 2 plus 1, or you could have 3 plus 1 plus 1, right? You could either have 1 triple root, or you could have 2 double roots. Okay? Some people call this a severe variety. Adults call this a severe variety, and this a Hessian locus. Okay, so the nodal locus and the Hessian locus. So here now we go like this, and here we go like so. Okay, but now more things can happen, right? These are the codimension 2 strata. So in codimension 3, well, you could have 3 plus 2 or 4 plus 1, and that can happen either like so or like so. So let's draw that. You can have a fourfold root and then one single root, or you could have a triple root and a double root. And the way this could degenerate is like this, or, you know, you have a fivefold root. Well, that's 5, okay? So we get the partition lattice. Yes, question?
But if you take these multiplicities into account, is it still given by this transform?
Say it again, sir.
So if you're taking the multiplicities into account when you're in this transform, and you add up all of the zeros from the multiplicity, is it still going to...
It's always 5, yes.
Yeah.
That's always true, yes, yes. So the number, that's true. So this is always true, absolutely. So, okay. Okay. In the sense of intersection theory, it's true, right? Period. Any two conics in the plane meet in 4 points. Period. Any two circles, okay? Try this on your high school, you know, if you're tutoring high school students or freshmen, right? Any two circles in the plane meet in 4 points. Period. Regardless whether they're special or on top of each other, any two circles meet in 4 points. So in the sense of intersection theory, period. This is just, you know, in applied algebraic geometry, this is a little easier to state. But in an intersection theoretic sense, we don't need expected. Okay? But I just wanted to show you, I mean, the level. I mean, here we're just having generic system. Here we have the discriminant. But there's a very, very interesting stratification. So even for polynomials in one variable, right, we have these various loci in the discriminant, codimension 1, codimension 2, codimension 3, codimension 4. There's a very, very interesting stratification. And in each codimension, each of these strata has a degree, has a prime ideal, has a syzygy, Betti table. I mean, you can study this, okay? And it's a very interesting topic. Tropicalize this. The sky is the limit. Okay. But let's stick with Bernstein's theorem. So here are some corollaries.
Why do you call these things mixed?
Oh, why is the discriminant mixed?
Yeah.
Well, it's the discriminant of two polynomials in two variables. So usually when people talk about discriminant, they speak about the discriminant of one polynomial in many variables. So that's the locus where the hypersurface acquires a singularity. That's usually the term of the discriminant. And we're using the term mixed discriminant to refer to n equations in n variables. But they're very closely related. It's a little bit like chicken and egg. Right, so. Okay, so there's Bernstein. Here's two corollaries. So first corollary, so if P and Q are lattice polygons, then M of P and Q is a non-negative integer. So this is not true. I mean, this is not clear a priori, right? Because we have the Minkowski sum, we have the area of the sum minus the sum of the areas. A priori, that's a half integer. Could be positive or negative, but a posteriori, it's a non-negative integer. 2, well, let's note that Minkowski sum is bilinear. It's a bilinear operator with respect to Minkowski sum. Minkowski sum, again, which you can actually infer that. So if you didn't know, if you did not know that the mixed volume is a bilinear operator. So the mixed volume is bilinear, right? So what I'm saying is that m of p plus p prime, comma q is m of p q plus m of p prime and q, and it's symmetric too. It's both symmetric and bilinear. Okay? Well, if you didn't know that, right? So suppose you have a system of equations. So let's take g times g prime equals h equals 0, right? You want to count the number of solutions of such a system where the first equation factors, right? Well, the number of solutions is the number of solutions of g and h together with the number of solutions of g prime and h. Right? So you can use Bernstein's theorem to derive these things, but of course you can also derive them directly. Okay? Let me do one more thing, is how to derive Bazoo's theorem. How to prove Bazoo's theorem. Well, we can derive Bazoo's theorem from Bernstein's theorem. So we can use Bernstein's theorem to derive Bazoo's theorem. So Bazoo's theorem, we have two polynomials that are dense. So we have a dense equation of degree d. Right, so Bazoo's theorem says if I have a general equation of degree d, another equation of degree e in x and y, then the number of solution is d times e. Okay? Well, you can do this algebraically, right? So I have a second polynomial here, and then we can calculate the mixed volume. Well, the Minkowski sum is a big triangle of area of side length d plus e, right? Well, how do you calculate the area? It's base times height divided by 2, right? So we have a half d plus e squared minus a half d squared minus a half e squared, and that's d times e. Okay? So Bazoo's theorem is a consequence of Bernstein's theorem, right? Because this simplifies to d times e, the number of solutions for dense equation. But you can also see this pictorially. You can draw the blue triangle here, and you can draw the red triangle there. And then, well, we're left with a rectangle of size d times e. Okay, so Bazoo's theorem is a very, very, very special case of Bernstein's. And let's take a 5-minute break. We'll continue at 11:00.